Yeah, these are already kind of.
Thank you. All right, we will begin. The clock strikes 8. Okay, so this is kind of a continuation of the problem we were doing on Friday. It was this problem, we were given points P, Q, and R. We wanted to find the cross product between the vectors joining PQ and PR. Okay, really the question actually said find a vector that is perpendicular to the plane that contains these 3 points. Then us being clever, we realized that, hey, we can achieve such a result using the cross product. First, we need to take some displacement vectors, and then we need to take the cross product between them. That will give us what we want, a vector that is perpendicular to this plane that contains these 3 points. Next, we can go further. Here's another question we can ask. What is the area of the triangle with these following vertices, P, Q, and R? Okay? And to answer this, we must talk about this phenomena that we have talked about already. I think we've talked about it already. Yes. Yes, we have. We talked about how, let's say we have a vector A and we have a vector B. Okay. Notice that you can construct a parallelogram based off of the vector A and the vector B. The area of a parallelogram is actually equal to the base times the height or the altitude. Right here, this height. Notice if this is some arbitrary angle theta, this makes a right triangle. And out of this right triangle, we have a magnitude triangle like so. Okay, where this is some unknown x. We don't really care. Really what we want to know is what is this h, right? Because then we can calculate the area of a parallelogram. How does this relate to a triangle, you ask? Well, notice that a parallelogram is technically two triangles, right? It's this triangle. Make a copy of it, flip it upside down, paste. That area is a parallelogram's area. So it's two triangles. Matter of fact, the area of a parallelogram being able to base times height comes from 1/2 base times height plus 1/2 base times height. Adding these together, you get 2 base times height over 2. 2's cancel, so you just get base times height, right? Very good. Now, notice if we utilize trigonometry here, sine of theta is equal to opposite h over hypotenuse, magnitude of our vector b. And when we solve for h, what do we get? Sine of theta. Yes, yes. Because we want to know the y value. We're going to use the sine function. So notice that the area of a parallelogram here, this a is equal to base times height. A is equal to base. Notice that that is just the magnitude of the vector a. Boom. Height, we calculated. That is this magnitude of b sine of theta. Oh, but take a look. What does that look like? This part of the equation, what does this look like?
Cross product.
Yes, it looks like the cross product between the vector A cross the vector B. But it's not a vector, right? This is a scalar quantity, right? There's no like final direction vector like that. That's not there. It's a scalar quantity. So we take the magnitude. So it's the magnitude of the cross product, okay? So in order to find the answer to this problem, all we have to do is find the magnitude of this cross product and half it. Because we want to know what the area of the triangle is based off of these vertices. We know that the vectors, the displacement vectors PQ and PR, you can almost call this PQ and call this PR, right? All we got to do is take the magnitude of this cross product and half it, and you will get what you're looking for. You will get the area of the triangle with these vertices, okay? So let's do it. What is the magnitude of this? Well, it's quite simply its components summed together squared. All right. I can't really do that in my head, nor would I be impressed with myself if I could do it in my head. But what you end up getting is 5 square root of 82. And remember, we wanted to half it because we want to know what is the area of the triangle, not the area of the parallelogram. So we half it. That's our final answer. So, I mean, this is just an application of that very interesting phenomenon that the area of a parallelogram is somehow related to the magnitude, which is the length of the cross product vector between two vectors that generate the parallelogram. It is astonishing because if you think about it, one of them is just a length. It's a one-dimensional quantity. The other one is an area. It's a two-dimensional quantity. But the magnitude of the one-dimensional quantity and the two-dimensional quantity are the same. There's something to that stuff. Maybe there's mathematicians who figured it out. Maybe there isn't. I don't know. I can't tell you. But there's something to it. As my gut feeling, my intuition says that there's some deep truth hidden in that correlation. Now let's talk about triple products. This is really cool because it is the three-dimensional generalization of this phenomena with the parallelograms. So let's say we have this situation here. Okay. Let's say we have some vector A, some vector B, and some vector C. All right. We're in R3 now. This is an R3 situation because we're in Calc 3. So notice that the base can form a parallelogram. This needs to be like slanted. This needs to be slanted. This needs to come through here. This needs to come through here. This needs to come through there. That needs to go through there. I feel like the dots are not visible enough. We will utilize squigglies. I will use squigglies instead of dots, and that will distinctify them, just give them distinction between the line with the vectors here. So notice, what shape does this make? If the base cross section of the shape is a parallelogram, what would be the three-dimensional analog of this parallelogram? A three-dimensional parallelogram, right? You guys know what that's called? It has a special name.
Paralleloid or something.
Close, yeah. That's very close. I mean, that was a very good guess. It's a parallelepiped. Yeah, it's just the name, you know. We could have called it a paralleloid, you know. If you got to the shape first and you got to name it, you could have named it paralleloid, and history would have been changed, and it would have never been called a parallelepiped. But you know, names are just arbitrary. But we'll make sure you know that that's what mathematician folk call it. Now let's talk about the triple product. This is when you get this kind of a situation, and you say, okay, I want to take the vector, I want to dot it with a given situation here. So because B is going like this and C is going like that, notice that the cross product between them will be emanating out of the board. Versus if I take C cross B, the cross product will be going into the board, okay? So we'll just take B cross C. As you recall, you know, A cross B, they don't commute, but they anti-commute, okay? So at the end of the day, all that would change is a minus sign, but we just want to keep it like this. Actually, your book constructs it like so, so we want to go with that, just in case you want to look at it that way. We then notice, let me move this A over here, and let's create a straight vertical line here, okay? This might quite possibly be, let's say, the z-axis, okay? And we can find some angle theta here. Notice that just like with the parallelogram, the area was equal to base times the altitude, or the height. Similarly, the volume here is going to be base times height times something, okay? I've left a space there. Really, what it's going to be is this cross-sectional area right here. Remember this area, B cross C? That's what's going to go here, okay? And remember, this base is a one-dimensional quantity. It's just a length. That height is a one-dimensional quantity. It's just a length. So we need this area over here. So maybe I might scoot this over right here. And so that area is generated. Notice that we've already discussed that the area of a parallelogram is the magnitude of the cross product between B and C. So we can just have it like that. Then we need to calculate what is this height here. And we can utilize trigonometry. Notice if I pull that triangle out, get a right triangle here, get a theta here, okay? Notice, oh, let's make it a magnitude triangle. Notice what happens when I take the cosine of theta. That is the, let's say this is the height, right? That is the adjacent to the angle divided by the hypotenuse. And then we can solve for the height because that's what we aspire to plug into our equation for volume of the parallelepiped. And so solving for h, I get this is equal to the magnitude of A cosine of theta. We can plug this in right here. So volume is now base. Well, I'll just put this here, magnitude of A cosine of theta. That was what we replaced for height. So base is going to be here. Okay. You will soon see that this triple product will correlate to the volume of a parallelepiped, just like how the cross product's magnitude correlated to the area of a parallelepiped. And notice that before, B cross C gave us a vector, so we had to take its magnitude to get a scalar quantity. Here, your book writes magnitude at the end of it, but that's kind of just to make sure you don't have negative volumes. Really, when you take the dot product between two vectors, this whole thing is a vector, this is a vector. When you take the dot product between two vectors, you're going to get a scalar anyways. That magnitude business is making sure you don't get a negative volume. Okay. What does this look like to you guys? This equation right here. Based off of the operations we have studied so far between vectors, we got the scalar product, also known as the dot product. We have the vector, we have the cross product, which is also known as the vector product. Doesn't that kind of look like something along those lines there? Notice that the volume equation looks very much like, let's say, B cross C dot A times that base, right? And we take the magnitude here as your book notes. You guys see what I'm talking about? Notice that the base length is over here in this equation. And actually, when I write base here, I need to delete this base here, and I need to delete this base here, because to get the volume, you need a length times a length times a length. And notice this was already a length times a length because it was an area. So you multiply it times the height. So I reproduced that base and I didn't need to do that. So just rewriting that volume over here. Notice that this is as if you're taking the dot product between A. Yes, you get volume, magnitude of A, magnitude of B cross C, cosine of theta. That's right here. And delete that base here. I don't want a 4-dimensional parallelepiped. Okay. Now it can be shown and proved, and we're short on time, and I would love to prove that, but we're very short on time. But notice that we can prove this result. So it would be a very fun exercise, and it might show up on the homework to do that. Or it might not. I encourage you to go prove that whether it's on the homework or not. Okay. Furthermore, in the book, it highlights a proof where you have A dot the vector B cross C, for instance, and let's put parentheses to avoid ambiguity. it shows that it ends up equaling the determinant of this matrix. Okay? And you guys remember how you take the determinant of this matrix? You just do cofactor expansion. No, you do that, you know, cover this thing up, make it a 2 by 2 determinant here. Cover this thing up, this row and this column, 2 by 2 determinant, and then cover this row, this column, 2 by 2 determinant. We've already reviewed that, but it can be shown that it would reduce to this 3-dimensional determinant. Now, let us apply this knowledge, because I'm sure you're wondering, why is this useful? Well, mathematicians don't really care whether something is useful. We just study it because it's beautiful. It just so happens that this Calc 3 stuff is very useful. Matter of fact, it was invented for physics, to solve physics problems in electricity and magnetism and fluid dynamics. But nevertheless, we can use this triple product here to show this fact. Let's say I have some vector defined by these values. I have 3 vectors defined by these values. A is equal to this, B is equal to this, C is equal to this. Okay. So the question is, are they coplanar or not? Are these vectors coplanar? Okay. Remember, I deleted the picture. Here's our, let's say, our arbitrary A, arbitrary B, arbitrary C. You know how I can make a parallelepiped out of this situation. This comes here, this goes over there. Oh my goodness, this parallelepiped is really bad. So let's go like this. Okay, it's not as good as before, but imagine that that is a beautifully artistically and to scale drawn parallelepiped. Okay, notice that A, B, and C are vectors that are pointing at something, right? These vectors have arrows, and the tips of the arrow point at a location in 3-dimensional space. What would the volume of a parallelepiped be if the location of these 3 points was coplanar, meaning that they lie on the same plane?
0.
Correct. Because then this shape would be flattened. It would actually be just not a parallelepiped, that's for sure. So just like how we could use like the dot product to determine if A dot B is equal to 0, just like how we can use the dot product to test whether something is perpendicular, the 2 vectors are mutually perpendicular to each other or not, this is kind of a test to see if whether they're coplanar or not. Just one of the many uses of this mathematics. Okay. So how do we do it? It's from what I told you earlier that I erased. It's from the triple product that we can take. And it can be shown, it's actually not, it doesn't require that many steps to show this. That reduces to this 3 by 3 determinant. And so let's find this determinant. We will cover up the row and the column here, and we'll put an I hat. So I hat here. Oh, and let's not put arbitrary values. So this is what that equals, but I have explicit values for all these entries. So I have 1, 4, -7. I have a 2, a -1, and a 4. I have a 0, -9, and an 18. Okay, so we will play the 3x3 determinant game. This is how you play it. I know we've reviewed this already. You put an I-hat, you put a 2x2 determinant, and you cover the row and the column here. What remains is this stuff: -1, 4, -4, -9, 18. And remember, we put a minus j hat. This has that minus sign is a consequence of geometry, but also some algebra. We discussed that. So we cover this up. We put the 2, 4, 0, and 18 plus the k hat. Cover these up. So I get a 2, -1, 0, -9. And then we proceed to take the determinant of these values. Now notice this was when we had I, J, and K over here, but we don't. We have A1, A2, and A3 because of the dot product. So we're going to replace this I here with the first entry of A. And we're going to replace this J here with the second entry of A. And we're going to replace this K here with the third entry of A. So back when we had I, J, K here, let's say B1, B2, B3, C1, C2, C3, we're still doing the same thing that we're doing right now. It's just the first row is different, okay? In the triple product, the first row is now the entries of the vector A. In, let's say, taking the cross product between B and C, the first row was the entries of the basis vectors, I, J, and K, okay? So this reduces to -1 times my 18 minus my -9 times my 4 minus 4 times 2 times 18 minus a 0 because 0 times anything is 0 minus 7 times 2 times a -9 plus a 0. 0 times anything is 0. And then you do the arithmetic, or you tell Maple to do it. You could tell anybody to do it. You could do it, or a computer could do it, or a computer algebra system, or a calculator. Either way, the calculations will reduce to it being equal to 0. And as this young man pointed out, that implies that the volume of the parallelepiped is 0, meaning we have effectively proved that these three vectors are coplanar. If they were not coplanar, the volume would not be 0. So that's a very cool application of this math magic. Okay. Oh, and there's a really cool relation at the end of the chapter that, again, I wish I could prove, but might just leave it to a homework exercise, or I can do a YouTube video about it. I've been telling you guys that I'm going to upload YouTube videos about the proofs of these things. But at the end of the chapter, you'll get this relation that can be proved using the knowledge that you guys have. A cross the quantity B cross C is equal to A dot C. This is going to be a scalar, right? So it's going to scale B like this, minus A dot B. This is a scalar, so it'll scale C like that. So it's very interesting. A dot C will scale B this way. You subtract that from A dot B scaling C this way, and somehow that's equivalent to A cross B cross C. Matter of fact, this implies we have to take B cross C first, order of operations here, and then we cross that with A. But it's very interesting how this relation is true. Mathematicians love this stuff. We love not only discovering this stuff, but proving that that is the case. Oh. Okay. I will put this proof on YouTube. Haven't done it yet, but I will. I promise you. Okay, and your homework for this section, I will post on Canvas. Now, let's move on to a very exciting section. 9.5. Lines and planes in R3. Okay. In 2 dimensions, how did we talk about lines? Okay. We had our x-axis, our y-axis, and we have a line here. We call this, y of x is a function of x is equal to mx plus b, right? And that's it. There's 2 ways to create an equation for the line. You either get 2 points, calculate the slope between them, and then you can generate the equation of the line, or you can be given a point on the line, given the slope, and you can generate the equation of the line. Okay? Things really aren't so different in R3. Okay? If you really get down to it, things really aren't that different in R3. They seem different. They seem fancier and more complicated, but they're really not. Okay. Let's say you have some 3-dimensional line in R3. Okay. Now we define this O as the origin, and we can define a vector with starting point the origin, emanating out and touching some portion of this line L. Okay. Right? Okay. We call it R naught. The vector R naught, let's say it has these values, x naught, y naught, z naught. Y naught is not the question WHY naught. Naught just means like it's a historical notation of original or starting point. I think of it as original point, and that helps me remember it. Then notice that we can have, if I move this R naught, I wouldn't have to create a curvy line. That is annoying. Okay. Then let's have another vector. Call it R. So R naught touches here, R touches here. Let's define this vector R as having these components, x, y, and z. Clearly they're arbitrary in nature, because this line is an arbitrary line. Okay? Now, notice that we can define a vector over here. Really, I can assign points here. I can say this is P naught, and I can say this is P. So this vector connecting P naught and P would be their displacement vector, right? Okay. Your book calls this displacement vector the vector A. Okay. But really, A is the displacement vector between P naught and P. Okay. Then we have to define one more quantity. We define this quantity V. Okay. This quantity V is a vector that is parallel to this line L. Okay. And V and my R's and my V's look very similar. So if you guys have any questions as to what is that an R, is that a V, let me know. I try to accentuate the curve on the R, but sometimes I fail. So please let me know. Yes, ma'am.
I put a hat on my V.
You put a hat on your V?
Yeah, so I'll write like that.
Oh.
On the left side, like a little.
Okay. I would really appreciate it if you showed me that notation, so that I will adopt that notation.
I'm using my V.
Oh, you mean like this, like?
Yeah, something like that.
Oh, okay. That's a good idea. It's a very good idea. That will help. I'm actually going to adopt that from now on. Now the V looks like it's flying. All right. So we've defined these vectors here. I have the list here. I might as well include A over here. A is really the displacement vector between P naught and P. Okay. Notice through vector addition that the vector r is really the resultant of two vectors being added to each other. Okay, r is the result of r naught being added to this a, right? It's just vector addition. First day of class, or second day, or something like that. Very early. It's just vector addition. Notice, here's the key, here's a very key idea here. We define V to be a vector that had components that made it parallel to the line L. Notice that we can scale such a vector by a real number, t, a parameter, if you will. So let t be an element of the reals. We're going to scale this v, we're going to multiply and make it not b right here, but we're going to scale it to where it's perfectly the same as a, the vector a. And we can find such a number because they're parallel. We can find such a number, it exists. So notice that our equation here, r is equal to r naught plus a, can be reduced to r is equal to r naught plus tv. Okay? Now, and you guys have this recorded, so I'm going to have to delete some, I'm going to have to create some real estate here. Okay. Notice that if we break this apart now, r is equal to component-wise x naught, y naught, z naught, plus, this is now TA, TB, EC. Okay. And then when we add them component-wise, I get this is x naught plus TA. This is y naught plus TB. This is a z naught plus TC. Okay. Notice that all equals r. R equaled this. So I can set the x component here equal to the x component there. The y component here equal to the y component here. The z component here equal to the z component here. Meaning I get, let me erase. I get something very amazing here. I get x is equal to x naught plus TA, y is equal to y naught plus TB, z is equal to z naught plus TC. What does this look like to you? That's right. It looks like y equals mx plus b, right? Notice that, for instance, y, I could replace this with y of t. Y as a function of t. The slope is now this number in front of the variable, and the y-intercept is now this right here. Notice that we have decomposed it as a line parameterizing the z-coordinate, a line parameterizing the y-coordinate, a line parameterizing the x-coordinate. And what is the parameterization here that we're talking about? It is precisely the number t. The real number t is our parameter. This parameter can vary, okay? Hence why y of t, x of t, z of t can get formed here. It is a parameter. It can vary. It can be equal to 0, -1, pi, 36, -5 billion. And whenever you plug those values in for the parameter t, it will then, the vector that points to L will change where it's pointing. Matter of fact, cool enough, if you start off here, then you start off here, wherever you start off, that's really t equals 0. And so to the left of that will be inputs for t that are negative. And to the right of that will be inputs of t that are positive. Okay? Cool enough here, in 2 dimensions, we had a scalar quantity for the slope. Slope gave us a means of quantifying via a magnitude, a scalar. But now, this vector v is kind of behaving like this three-dimensional slope here. Okay, because remember, the original equation we've been talking about. And even this can look like y is equal to mx plus b, can it not? Notice that this vector r is a function of t, is it not? Correct? Oh, and I broke my promise here, but I will not break my promise. I broke my promise about the notation. You guys see that? It's like a y equals mx plus b, but a three-dimensional version. Here's the x, the t. Here's the slope, our vector v. Okay, and what is this then? Behaving analogous to the y-intercept in 2 dimensions, analogous to that. Really, we don't have a y-intercept anymore. We have kind of a starting point in 3-dimensional space. But in 2D, that's what it looks like. And in 3D, it looks different. But they're really so connected. And so the way we decompose this parametrization and these equations that we were able to extract, these are called parametric equations for the line. Making sense? Good. The more this makes sense, the easier doing problems with like this stuff will be. Okay. Now that we've discussed that these are the parametric equations, let's apply them to a real problem with real numbers. Now that we've gone through this construction in painstaking detail, application of the construction will be nearly trivial. Right? It'll be nearly trivial. Because really all you got to do is add, subtract, divide, multiply. At the end of the day, once you know how it relates. So let's say, here's an example. Find a vector equation and a parametric for the line L that passes through this point right here. Let's call it P. It's equal to 5, 1, 3. Okay? And there's an added piece of information, and it must be parallel to the vector. I'll call this vector V, if you will, equal to, I can't break my promise here, 1, 4, and a negative 2. And this chalk is getting very low on length. So let's get a new piece of chalk. Okay. Drawing this out here, if you wanted to draw it out, and that's always a good idea. If you're stuck, if you don't have an intuition for something in math, draw a picture. Draw a picture. If you don't have an intuition for something in math, get some paper out, get your writing utensil, and somehow try and visualize it in terms of a picture. I guarantee you it'll give you more of a fighting chance than just sitting there and being perplexed. So let's draw a picture, okay? Let's say this point P is that point over here, 5, 1, 3, okay? And here's our R naught, right? R naught is our initial vector. That's our starting point, and that's our initial vector. And then notice that V runs parallel to the line. Okay, that's our V. I already told you what V equals, so I don't need to actually write its 3 numbers. All right. Okay, we need to use the vector equation here. Because it said, find a vector equation, and then we'll move on to parametric. Find a vector equation. Notice we are given the, we can find R naught, right? R naught has a starting point, the origin, and ending point, P. So notice R naught is really a displacement vector where it goes from O to P. And we do final, 5, minus initial, final, minus initial, final, minus initial. So clearly we've derived something relatively trivial, but that's how you can find R, and that's the method to find it. Notice that if it didn't start from the origin, you can't do those entries being 0. These would be non-zero values if it didn't start from the origin. But because it does, we get this relatively simple result. So that's what will go here. And we know V. So let's go. Let's combine them. That means R is equal to, component-wise, R naught, which is 5, 1, 3, plus VT. What is V? Here. T is just going to go to each of its components and scale it by T. T is a scalar, and it scales each portion of the vector, the X, the Y, and the Z, by multiplying 5 of its components. So we get T here, we get 4T here, and we get negative 2T here. Okay? And now all we have to do is just add the components to get the new vector R. And I'm going to have to clear this space up here. And in the drawing, the way I had it, that was really VT, which I drew V. I really should have called it VT. But hindsight is 20/20. So R is equal to 5 plus UT, right? Because we add 5 to this component, comma, 1 plus my 4T, comma, 3 plus my negative 2T. I could just shorthand write it like 3 minus 2T. Done. That's the vector equation, because we have the equation for the line in terms of a vector. Now, let's do the parametric equation for the parameter. T is our parameter. Really, it's not that bad. Notice that all this stuff is equal to R, and R is equal to some X, Y, Z. Set each of the components equal to these components. X is equal to that, Y is equal to that, Z is equal to that. So X is equal to 5 plus the T. Y is equal to 1 plus the 4T. Z is equal to 3 minus the 2T. And there you're done. You have your parametric equations. Notice X is a function of T. Y is a function of T. Z is a function of T. So the cool thing is we've effectively been able to describe the X, the Y, and the Z components of the line, how it changes via just one parameter, the parameter T. And in 2 dimensions, Y equals mx plus b, X was behaving as T. We were describing the Y. That's the only thing we had to worry about. We were describing the Y with the parameter X. But now we've grown up and we're on to bigger and better and more complicated and more fun, because it's more complicated. When it's more complicated, it's always more fun. When it's more challenging, it's always more fun. 3-dimensional calculus. And so now we have to know how to parameterize the X, the Y, and the Z off of a common parameter T. And notice we can actually eliminate the parameter as well. You guys have done this before. Eliminate the parameter of a parametric equation. Let's see how I'm doing on time. Now I got 3 minutes. All you would have to do to eliminate the parameter for T is to solve for T in each of these equations and then set what is not t all equal to themselves because they're all t. T is equal to t, which is equal to t. Okay? You'll see what I mean by that here in a little bit. But this problem is not done, and we're not eliminating parameters yet. That's just some foreshadowing. So we've done all this stuff. Here's another question, or another command, if you will. This textbook, written by Stewart, likes to command us, find this, find that. But really, we're not being bossed around. We are gladly being trained by this person teaching us calculus. So they're not bossing us around. Now they're saying, okay, here's a two-part question. Find two distinct points on this line. And yeah, not P that you were given. You know, points on the line that are not P that were given. So how would we do that if X is a function of T, Y is a function of T, Z is a function of T, and all of these are points on the line for various T? How can I find some distinct, non-trivial points on this line? Absolutely correct. Two. Let's do it. So, so for t equals 2, x of 2 would be the x component. So here's your 7. Y of 2 would be your y component, which is 1 plus 4 times the 2, which is an 8. 8 plus 1 is a 9. And the z component, that's 3 minus a 2 times a 2. That's 3 minus 4, that's a negative 1. Voila! You have your point on your line. And this new point, we'll say P sub 2, if you will, for my notation. It's 7, 9, negative 1. That's another point on the line. Pick another value for the parameter t, you find another point on the line. And you know, that's about all. We have 1 minute, and that's about all the time we have is to actually do one more parameter. So pick a number that's nice, because you guys know I'm not that great at mental arithmetic. That's not my forte.
0. Oh.
0? Okay. Accept that number, because 0 would just give us our original point P. Notice, actually, I'm glad that you suggested that, because notice that t equals 0 gives us our original point P. You see that? If t equals 0, this becomes 5. If t equals 0, this becomes 1. If t equals 0, this becomes 3. Yeah, 1. Yeah, thank you. You were being kind by picking the best number to do arithmetic with, 0. But we have to find two non-trivial. But I'm so glad that you said that, because you notice now that at t equals 0, you get your starting point. And at t equals negative values, you get your what happened before. And at t equals positive values, you'll get what happens in the future. And I make air quotes, because it really is not really the future, but t is called t for a reason. This mathematics was invented for physics, and t really can stand for time, if you will. It's kind of like a dynamic line. That's how I like to think about it. Mathematically, it does not represent the quantity time. It is just a parameter. It's just an element of the real numbers. But in physics, when you apply it, it can realistically represent time. So the way you find another point, pick, let's say 1, plug it in, you find the values. It should be like 6, 5, 1. Your homework will be posted promptly online, and the lecture will be posted promptly online. And grading, I have not graded a single assignment for you guys yet, and that is due to many factors. I will work on that immediately. I will start to give you guys feedback. One thing that I can do is upload my solutions to the homework. So I'll show you how to do every problem. And that way you're getting some kind of feedback already until I can actually grade them. All right? Sounds good? Keep up the great work. I'm so proud of all of you. Oh, and thanks for joining us, Caleb. I see you there at home. Well, I don't really see you, but I know that you're listening.